Welcome to the afternoon session. Our first speaker is Kuan Wen Lai from Taichung University, and he'll tell us about Frobenius Nonclassical Hypersurfaces.
It's Tunghai University. Tunghai University. Thank you. It's my pleasure to be here, and I'm happy to see so many familiar people in this classroom. Today I'm going to share with you some, like previous talk today, something over a field with positive characteristic. And actually, in my talk, everything will be over some finite field. Yeah, over some finite field Fq, where Q is a prime power. Okay. So let me start with some definition. What is a Frobenius non-classical hypersurface? It's defined as follows. So consider a hypersurface defined by some homogeneous equation in Pn over a finite field Fq. Now we say X is Frobenius non-classical. Let me abbreviate it this way. Frobenius non-classical. If its defining polynomial divides, if it divides another polynomial which we denoted as F10 for some reason. It's defined this way. It's the summation from I to 0, I equals 0 to n, of xi to the q times the partial derivatives of f with respect to xi. Here xi's are homogeneous coordinates of the projective space. Yeah. So a hypersurface is Frobenius non-classical if f, the defining polynomial, divides that polynomial. This is algebraic definition, and geometrically you can view this condition this way. So we don't need to assume X to be smooth. No. Yeah. But our main result concern only smooth Frobenius non-classical hypersurfaces. Yeah. So, like geometrically, if you consider, say, let phi or maybe phi q to be the Frobenius q's power action, maps x0 to xn to erase every homogeneous coordinate to q's power. Okay, consider this Frobenius endomorphism. Geometrically, this condition means that for every point on the hypersurface, okay, here a point don't need to be defined over the ground field. You can make it to be a point defined over a direct closure. So for every geometric point, its image under this action, which is still a point on the same hypersurface, lies on the embedded tangent space at P to X at P. Here, let me make the notation more clear. So here TPX is defined this way. The embedded tangent space. Sorry, I missed something. Okay, the embedded tangent space. Yeah, the xi sum to I from 0 to n, where the coefficients are partial derivatives evaluated at the point P. Yeah, so if the point P is smooth, this is the unique, this is the tangent hyperplane tangent to P, tangent to x at P. And if P is singular, then this is just the total space. Yeah, so geometrically, Frobenius non-classical means under the Q's action, a point P is always mapped by the Frobenius action. Its image always lies in the tangent space in the previous point. Okay, so maybe let me give you some examples. Yes?
If you divide one equation by the other, you get some polynomial of degree q minus 1, right? Does it have some geometric meaning?
Can you say again?
So if you divide f10 by f, right? Assume that f divides f10.
Huh? Yes?
You get a polynomial of degree q minus 1.
Yes.
Does it have any geometric meaning?
That's a good question. Let me think. Yeah, I've never thought about this. So far, we only focus on the hypersurface itself. Yeah. But I think I'll mention something. I don't know how to answer your question now, but maybe later when I go back to this again, maybe I can say something. Okay, maybe let me give you some very explicit examples. Okay, I'll give you two very standard examples. And the first one is this one. Okay, so this guy defines a smooth surface in P3. And it's very easy to check this guy is Frobenius non-classical because if you compute F10, this is the result. So you get x0 to the q times the partial derivative of this guy with respect to x0, which is this term. And you do the same thing. And keep doing the same thing. Okay, you'll get something like this, and you'll see that all of these cancel with each other, so you get 0. Yeah, and because everything divides 0, F divides this guy, so it's Frobenius non-classical. And this is a quite special case. Yeah, and we have, in our main theory, we'll get some, we have some characterization about Frobenius non-classical hypersurfaces satisfying these properties, F10 is 0. This is one of the two examples that I want to mention, and this example is also interesting partly because also first of all you can, of course, easily generalize this kind of example to any higher even dimensions, and this example is also space theory. In the sense that every FQ point, this is X, every FQ rational point on X, this set is the same as all FQ rational points in the projective space. Okay, or every rational point, FQ rational point in the projective space. Here I'm in P3, so let me just write this. Yeah. Every rational point in the projective space all lies on this surface. It's very easy to check. Okay, and here's the second family of examples, and they have a name called Hermitian varieties. But let me put a quotation mark around these varieties. Traditionally, they are called Hermitian varieties, but actually they are hypersurfaces. They are defined this way. So in this case, we need to assume Q of Fq to be a square. Okay, suppose you have a finite field with Q many elements where Q is a square, and in this special situation, there's an involution on the ground field which takes every element to x bar, which is x to the square root of Q. There's an involution. And it's defined this, it's denoted this way because people usually consider this as an analog of complex conjugation over a finite field. Okay, so with this, we say hypersurface X defined by some polynomial in Pn is a Hermitian variety, or just is Hermitian. Okay. If we can write its defining polynomial as in this way. Okay. So here I'm thinking about this x as a row vector. So this xt is the transpose, the column vector. In the middle, it's a square matrix. Here, H is Hermitian in the sense that we are familiar with. So it satisfies this property. And if you take the transpose, okay, so first of all, it's a matrix with coefficient in FQ. And if you take transpose and take bar, which means you apply this action to all of its entries, you get the same matrix. Okay, it's Hermitian. Yeah. So this is the definition of Hermitian varieties. However, there are two people. They prove that Hermitian varieties are actually very simple. So if you fix the rank of H and also the dimension, then up to PGL action over the ground field, they are all the same. And this is a result by Bose and these people, Chakravarti. Okay. So it says that up to PGL FQ. Okay. We can write we can find another expression for that polynomial. The expression is this one. For some R. Okay. Yeah, so this means that up to PGL action, actually every Hermitian varieties can be expressed by some Fermat equation. And once you fix the dimension and also the rank, which is R plus 1 of the square matrix H, then they are the same. Yes, and from here, you can easily check that F10, and you pick that F and compute F10 according to our definition. This guy will be this one. Okay, and this guy is exactly a power of this expression, the root of Q's power. Yeah, this, again, can be easily checked by hand. So in this case, F10 is a power of the defining polynomial. So in particular, polynomial divides F10. So this guy is Frobenius non-classical. Okay, so this is the second family of examples of Frobenius non-classical hypersurfaces. And in this talk, I'm going to show you, first I'm going to show you there's a degree bound for possible degrees of this kind of hypersurfaces. Once you fix Q, then the degree of the hypersurfaces has a lower bound and an upper bound, and they are sharp. And when the degree is maximum, we have some characterizations. And when the degree is minimum, we have some partial classifications. Now, that's the main purpose today. But before mentioning the main results, I want to tell you some motivations about why we care about this Frobenius non-classical hypersurfaces. There are two motivations. The first motivation, I call it a weak motivation. This is actually the true motivation which led us to explore Frobenius non-classical hypersurfaces, but it has loose mathematical connections to our main result. And later on, I'll introduce the second motivation, which I call a strong motivation. It has stronger relationship with our main result. Okay, so our weak motivation is about the so-called Bertini type theory over a finite field. Okay, Bertini type theory over a finite field. Yeah, so we know Bertini type theory is useful when we are trying to prove some properties on a variety by using reduction on dimension. Okay, and we also know over an infinite field, every smooth project variety has a smooth hyperplane section. But we also know that this theorem fails over a finite field because, for example, if you don't know an example, then my first example there is a counterexample over a finite field for the Bertini theory. Because in example 1, if you pick x and then intersect with any FQ plane, okay, so x is the surface there, and you intersect with any hyperplane. And in this case, it's a plane. You'll get a union of Q plus 1 many FQ lines. Meeting at one point. Okay, so that example provides a counterexample to Bertini's theory. Yeah, but still, Bertini's theorem holds over an infinite field. So it says, so it implies that once you pass to some field extension of your ground field, once the extension degree is high enough, you will get some smooth section. Yeah. So again, so Bertini theorem says asserts that although over finite field, once you pass to a higher degree, enlarge your ground field, make it large enough, extend it to be higher degree enough, you will get some, you will find some hyperplane section which is smooth. But the question, so here comes the question, how high it is? Can you get a smooth hyperplane section? And this direction, I think the first people studying this kind of problem in this direction is Particle. He has a result. So the result says that suppose you have a smooth projective variety. Of degree d over finite field Fq. The question is how large Q should be in order to get some smooth section. The answer is once your Q is at least d times d minus 1 to this power, dimension of x, then there's a smooth section. There is a smooth section over the same field. Yeah, and this result holds for any smooth projective variety. And we have an extension, I mean, a refinement of this result for hypersurfaces. Suppose X is a smooth Frobenius classical hypersurfaces, Frobenius classical hypersurface,
Classical means
not non-classical. Smooth Frobenius classical hypersurface over Fq of degree d. Okay, then once Q is at least 3 over 2 times d minus 1, dimension x minus 1, okay, then we get some smooth hyperplane section. Over Fq. Yeah, so this is some kind of refinement because in general you need Q to be approximately d to the dimension plus 1 power to get something smooth. And here in this case, you only needed to extend the ground field to be dimension x. Okay, sorry for this messy notation. Yeah, this you can reduce the degree by 1 to get some smooth hyperplane section for smooth Frobenius classical hypersurface. Yeah, and the key thing that makes this possible is that the key thing behind this proposition is that Frobenius classical means it's not Frobenius non-classical, and it means that the intersection between x and f10 equals 0. This is a divisor on x. This is a divisor on x. If it's Frobenius non-classical, so in that case, the defining polynomial of x divides f10. So x appears as a component of that hypersurface. Yeah, and the property that being Frobenius classical means that it's a divisor, and this allows us to bound the number. So in order to get some smooth hyperplane section, the method here is to, no matter here or there, is to try to bound the number of tangent hyperplanes. And tangent hyperplanes meet x on some, it's tangent to x on some spatial locus. And this condition allows us to bound number of rational points on this spatial locus, which in turn allows us to bound number of tangent hyperplanes. And once the tangent hyperplane is small enough, then you have a chance to find something smooth, some smooth tangent hyperplane, some smooth hyperplane section. Okay, and yeah, so because Frobenius classical has this nice property, this motivates us to explore properties about Frobenius non-classical hypersurfaces. This is the first motivation. And here comes the second motivation. Okay, so this is a strong motivation. And it's strong because it has direct mathematical connection with our main theory. Frobenius non-classical hypersurfaces was studied in the curve case by these two people, Hafez and Volosh. In 19, they have a paper called Frobenius non-classical curves. Okay. So say we have a Frobenius non-classical curve in P2, and say it's smooth. Non-classical. Okay. Of degree d over FQ. And in their result, you need to assume the characteristic is not 2. Okay. Assume characteristic is not 2, then we have some, and then they have degree bound, and they have some lower bound and upper bound for the degree, possible degree of such kind of curve. Okay. Yeah, I didn't provide many details here, but roughly, this is the result. Okay. Once you have a smooth Frobenius non-classical curve of degree d over FQ, then degree of the curve has to be bounded by these two things. Okay. The lower bound is quite clear. And upper bound is something with this expression. And they also have some classification result for smooth non-classical curve whose degree attains the minimum and also or the maximum. Oh, because you want this to be an integer, and like it's in such kind of sense. This divides this guy, so you get some integer. You want this to be an integer. It's a power of sun. Yes, yes, the same p. Yes, yes. Okay. Yeah, and yeah, it's continue of their result.
But your first example, basically Q plus 1, which is
That's a surface. Yeah. First, yeah, that's exactly the thing. For in higher dimension, you can get something higher degree, of higher degree. Yeah, and we can write down. They also prove that we can write down explicit equations for x, explicitly for d being max, but in this maximal case, the equation is very complicated. And I can also write down equation for d being minimal. And in this case, the equation is very simple, because in this case, namely when d is equal to square root of q plus 1, they prove that this curve has to be Hermitian. Okay. Yeah, so Frobenius non-classical curve, smooth one.
and what if Q is not a square?
What if Q, in order to be, then they didn't provide formula in that case. Yeah. If Q is a square and D is this, it's Hermitian. So you can write it in that way, in that Fermat way. Okay. Yeah. So here comes our main result. Okay, our main theory. So our main theorem is some kind of extension of Heffes-Volozhi's result to higher dimension. So suppose we have, again, some Frobenius, which is smooth Frobenius non-classical hypersurface over FQ. And yes, and suppose it's defined by some polynomial f. And say, suppose its degree is d. And assume degree is at least 2. Because every hyperplane is Frobenius non-classical. It's very easy to check. So assume it's not linear. And then we have similar degree bound, but the lower bound is the same, but the upper bound is a little bit higher. Okay. So in general, for any dimensions, the degree of a smooth Frobenius non-classical hypersurface over FQ has this lower bound and upper bound, and the lower bound is the same as the curve case. Upper bound is a little bit higher, and these are sharp bounds. And these are sharp. For example, the reason why the lower bound is sharp, sorry, this. Okay. Why the lower bound is sharp? Because we have the example, the second example, Hermitian varieties. If it's not squared, then okay. So here I'm saying when Q. Okay. Then I have no idea. Yeah, but when Q is square, we have this example. In this case, it's sharp. If Q is not square, I don't know if it's sharp or not. Yeah. And we also have some classification results when degree attains Q plus 2 or Q plus 1. And let me write them down. Okay, so first, when D is Q plus 2. Q plus 2, this case, occurs only when the characteristic of the ground field is equal to 2, and N is equal to 2. Okay. This means that X can only be a curve. Okay, so this is the case when D is the maximal possible number, Q plus 2. And if you compare this to Haffez and Boloch's result, they say the degree can be at most that number, which is definitely not strictly less than this number, but the difference is that there, the characteristic cannot be 2. And here we allow characteristic to be 2. So there are some examples with this degree. And let me write down some formulas. So say if there's such kind of example, then we have these formulas, and then I'll provide you some more explicit examples. So in this case, we can write f, the defining polynomial, this way. X, y, z times x to the q minus 1 plus y to the q minus 1 plus z to the q minus 1 plus some polynomial g here whose entries are x squared, y squared, z squared. Okay, so yeah, I need some yellow color. Yeah, so when the degree is Q plus 2, the characteristic has to be 2, and X has to be a curve, and moreover, it has to be described by such kind of equation for some polynomial G here, and you cannot put just an arbitrary homogeneous polynomial here. Yeah. But we have examples, such as you can put something like x squared, y squared plus x squared, z squared, y squared, z squared, plus x to the 4, y to the 4, z to the 4. Okay, for example, we have this very explicit example which shows you that this upper bound is sharp. Yeah, and this curve actually has a name, but it's not quite important to this talk. And the name is Dixon-Guralnik Z curve. Okay, some kind of curve with a name. Okay, and now I'll give you similar classification result when the degree is q plus 1. If you assume the degree is not, right, if you assume the characteristic is not 2, then the upper bound is q plus 1. And in this case, if the degree is q plus 1, we can also write down the equation for the hypersurface very explicitly. Yes? EG means you put this here. Yeah. I'm very sorry. This is for q equals 2. Q equals 2. Yeah. In q equals 2, we have this kind of example. Okay, and how about d equals q plus 1 and n odd? Okay, so when d is equal to q plus 1, there are two cases. One is n odd, the other is uneven. N odd means n is n of Pn. Or, yeah, in this case, the dimension of x is even. So in this case, we can write f, the defining polynomial for the hypersurface this way. This way, where this aij, they form a square matrix which is antisymmetric. Okay, for some square matrix which is antisymmetric, but because it's possible that the characteristic is 2, so we need to be careful what we mean by antisymmetric. So it means that, so first of all, the entries are all in the ground field FQ. And antisymmetric means this happens. So antisymmetric in the usual sense, and we also need to require the diagonals are all 0. Because if in characteristic 2, this condition is not enough to ensure that the diagonals all vanish, so we need to add this condition in characteristic 2. Yeah, so this is the case when the degree is q plus 1 and also when dimension of x is even. And the first example I provided in the very beginning belongs to this category. Again, so oh, yeah, non-degenerate. Non-degenerate. Thank you.
In that case, number 2 is also characteristic 2?
No, it's in general, any characteristic. Yeah, but I just want to say this condition is not redundant because in characteristic 2 we need that. Yeah. And yeah, like the first example I provided in the very beginning belongs to this category, and all such kind of examples are interesting because they are space filled in. All rational points in FQ all lies on such kind of hypersurface. And also, let me just mention it. If you take any FQ plane, P2, define our ground field and intersect them with such kind of hypersurface, you get, again, Q plus 1 many FQ lines meeting at one point. Okay, so now here comes the last case. If D is Q plus 1 and N is even, or equivalently when dimension of X is odd. Okay. In this case, so this case occurs if and only if the characteristic is 2. And up to PGL, we can write down F in the following way. Let me write down the equation here. Okay, so in this case, you can write F this way. X0 times some polynomial in the other variables. This is some G plus a part which is quite similar to the previous example. Xi to the Q times Bij Xj, where Bij also form an anti-symmetric skew symmetric matrix. Okay. Yeah, so every example belongs to the third category can be expressed this way for some G. But is there really any such kind of example? The answer is yes. So let me write down a very explicit example for you. So in this case, yeah, we found this example by computer. So first, let's write F4 as a degree 2 extension of F2 by element A, where A satisfies A squared plus A plus 1 equals 0. Okay, then the following example is Frobenius non-classical, smooth Frobenius non-classical, with that degree and N. So X times A plus 1 x4, x squared, y squared, x squared y z plus x squared z squared plus y to the 4 y squared z squared z to the 4 and then plus y to the 4 z plus y times z to a 4. Okay, very explicit but a bit long. Yeah, so this tells you that yes, indeed there are some examples belongs to the third category. Okay, and there's one more sentence in our main theory. Okay, there's one more sentence, which is moreover. Okay. F10 is equal to 0. This special case occurs if and only if we are in case 1 or case 2. Okay. Yeah, so the condition for being Frobenius non-classical is that the defining polynomial f divides this guy. And if this guy is 0, then you can write down the equation. You can, the hypersurface mass belongs to case 1 or case 2, and vice versa. If you have something in case 1 or 2, they satisfy this property. Okay, so this is the main theorem. And let me pause here for like 10 seconds. Is there any questions so far? Okay. If there's no question, let me continue. Remember in Heffes and Volo's result, when the degree of the Frobenius non-classical curve is minimum, square root of q plus 1. Q is a square. In that case, they can say the curve is Hermitian. How about in general? So in general, we can only extend their result to the surface case. Here are other results. Surface case, so if we have a Frobenius non-classical surface over FQ, degree D is square root of Q plus 1. Yeah, Frobenius non-classical. Okay. In this case, X is indeed Hermitian. I mean, you can find some PGL action, projection action, to make it in this form. Okay, so it's Hermitian. Yeah, but for higher dimension, we have no idea. So we can maybe, I can put this as open question or conjecture. Like, is it true that in general, in higher dimension, Frobenius non-classical, smooth Frobenius non-classical hypersurface of degree equals the lower bound square root of q plus 1, Hermitian or not? Okay, so this is a question. Yeah. Higher dimension. We have no idea. And the second other result is second minor result is, so if, again, X is Frobenius non-classical, suppose it has separated variables. Which means that the defining polynomial can be written down as a sum of two polynomials whose variables are distinct sets. Okay? So part of polynomials, part of variables belongs to the first polynomial, and the other belongs to the second one. There's no yeah. And these are, of course, non-zero. Okay. In this case, we can prove that the degree is 1 mod p. Where p is the characteristic. Okay, and of course you may ask why this result is interesting, because this is because smooth Frobenius non-classical hypersurfaces, they are non-reflexive. So first, it's proved by us in some earlier paper, smooth Frobenius non-classical hypersurfaces are non-reflexive. Non-reflexive. Here, non-reflexive means that if you consider the Gauss map from X to the dual variety, dual hypersurface in a dual projective space, which maps a point, any geometric point, to the tangent hyperplane. Okay. Tangent embedded hyperplane tangent to X at P. This map being non-reflexive means that this map is inseparable. It's inseparable. And there's a conjecture by Kleiman. Let me write it here. And this conjecture is made in this year, conjecture. So the conjecture says that every smooth, non-reflexive hypersurface has degree one mod p. Has degree 1 mod p, and here p is not equal to 2. Okay, so this is a conjecture, and this is known in a curved case, but not known in general. Yeah, so that's why the second result, that's why we care about the second minor result.
So in the curved case, are there projections of this type that are not for P2, but for curves of Pn?
Then I have no idea. I don't know. Sorry. Yeah. Yeah. Okay, so that's all what I want to say.
Questions and comments to Kuan Wen?
So I think in my examples that you gave, which are as type space filling, you can also always set that the F10 vanishes.
Say again the second. Can you say again?
So my question is like, is space filling, does it imply that F10 is 0?
Yes, space filling implies that. I would say no, but right now I don't have example in my mind. Yeah.
Other questions? Other interesting properties, for example, in terms of point counts, like whether these varieties, non-classical, have interesting point counting mod Q or something.
We have some possible interesting result concerning rational points on this kind of hypersurface. So the rational points on this kind of hypersurface, they form some kind of sets called blocking sets interesting in combinatorics. Yeah. Yeah, that's
What happens if you take project dual X check?
sorry, can you?
You said no differentiation, but if you take project dual
If,
or X check,
check.
check.
What is X check? X check is as a set, it's a collection of all tangent hyperplanes of X. Yeah. So you can also, or it's the image of this Gauss map to Pn. It's image back. It defines a map from X to here. Yeah. So this is a hyperplane in the original projective space Pn. So it's a point in the dual space. You map this to a dual space, and its image is this X dual.
So it's a reflection. But it's a terminology of non-reflection.
What's the definition of? Sorry. What's the question?
So my question is, what is the X check?
What is?
X check.
What is X check? In characteristic 0. Okay. Non-reflexive means that this doesn't hold.
Yeah.
Non-reflexive means that this doesn't hold. This is equivalent. What is what? What kind of variety?
Maybe it is given by F10.
I mean, this Frobenius non-classical hypersurface, they are all non-reflexive. Yeah, these are examples.
Still, I don't know some part is
Okay. We've never thought about this. That's a good question. We didn't. Yeah.
Okay, I think Kuan Wen again.